Hello, this is the section 4.5 lesson. In this section we're going to introduce the idea of confidence interval estimates for a population proportion. Okay? The basic idea behind this section is, as we've illustrated in the past two sections, that a sample proportion p hat is an estimate of a population proportion p. Now the number p hat is a single number, and so we call that a point estimate of p. Well, whenever we estimate something, we want a measure of the accuracy of our estimate. And so we're going to measure that accuracy in this section with two ideas. The first is called a margin of error. The margin of error is going to be a maximum distance between the actual value of p and the estimate. Or stated another way, it's like an upper bound on the error in our estimate. Now, we're never going to know the exact error in our estimate, because if we knew the exact error, then we would know the exact value of p, and there would be no point in trying to estimate it. Then once we calculate a margin of error, we're going to form a confidence interval. And a confidence interval is going to be a range of possible values of p, rather than just a single number estimate. But before we start calculating margins of error and confidence intervals, we need to define critical z-values. So start off, let z be have a standard normal distribution, and p be some number between 0 and a half. A critical z-value, denoted z sub p, is a positive number such that the probability that z is less than or equal to z sub p equals 1 minus p. So remember, these probabilities here correspond to areas underneath the standard normal density curve. And so this picture down here illustrates this idea. So here's our critical value z sub p. The area to the left of that is 1 minus p. And the area to the right is p. So again, from this picture we see that the probability that z is greater than z sub p equals p. And then by symmetry of the standard normal bell curve, if we have negative z sub p, which would be over here, the area to the left of it would also be p. So in terms of probability, the probability that z is less than negative z sub p equals p. So let's look at a couple of examples of finding critical values. Let's find z sub 0.025. So p in this case is 0.025. So by the third version of the definition of a critical z-value, the probability that z is less than negative z sub 0.025 is equal to 0.025. Now remember, the probability of this form is a value of the cumulative distribution function, the CDF. For the standard normal distribution, the CDF was denoted capital phi. So phi of negative z sub 0.025 equals 0.025. So to figure out the value of this critical value, we're going to go to our z-score table, table C1 in the appendix, and we look through the center of the table for an area as close to 0.025 as we can. And what we're going to find is that phi of negative 1.96 equals 0.025. And so if we match this up with our definition here of z sub 0.025, we conclude that the critical value z sub 0.025 is equal to positive 1.96. Let's do another example of finding a critical value. Let's find z sub 0.05. So by definition, we need phi of negative z sub 0.05 to equal 0.05. And so again, we look through the center of table C1 for an area as close to 0.05 as we can. And what we find is two areas, 0.0505 and 0.0495. And there's the corresponding z-values. And we see that both those areas are equally close to 0.05. And so we're going to take our critical value to be the average of these two positive z-scores. The average of those is 1.645. So there's our critical value z sub 0.05. So here's a table of critical z-values for some commonly used values of p. Now, p could be any value between 0 and a half, but these are some frequently used values. So we see here in our table, here's z sub 0.05 is 1.645. Right here we see z sub 0.025 is 1.96. We'll be referring back to this table frequently over the next few sections. And next we're going to discuss kind of a special case of critical values. And these special cases start off with a number alpha that's somewhere between 0 and 1. So then the number alpha divided by 2, which we'll call p, is a number between 0 and 1/2. And so then the critical z-value, z sub alpha divided by 2, is a positive number such that, so here in our picture we have z sub alpha divided by 2, and the area to the right of that is alpha divided by 2. And then here's negative z sub alpha divided by 2. The area to the left of that is alpha divided by 2. And so the sum of these two shaded areas is alpha. And so that means the area of the unshaded region here is 1 minus alpha. And so in terms of probabilities, the probability that z is between the negative z sub alpha divided by 2 and positive z sub alpha divided by 2 is 1 minus alpha. Now, don't let this subscript alpha divided by 2 scare you. Alpha is a number. Alpha divided by 2 is a number. And so this is z sub a number that's calculated and defined in the exact same way as we did in the previous examples. So let's do a couple of examples of finding z sub alpha divided by 2 for a couple of different values of alpha. So first let's take the value alpha equals 0.05. And this is a number that we're going to see a lot over these next few sections. And so z sub alpha divided by 2, 0.05 divided by 2, well, 0.05 divided by 2 is just 0.025. And so z sub 0.025, if we look down here at our table, there's our subscript 0.025. The value of the critical value is 1.96. And we're all done. Let's consider alpha equals 0.01. And so in this case, z sub alpha divided by 2 is z sub 0.005. And if we look at our table down here, here's a subscript of 0.005. The corresponding critical value is 2.576. And we're all done. So again, don't let that subscript alpha divided by 2 scare you. Alpha divided by 2 is just a number. Alright, so now that we've defined our critical values, we can define our confidence interval. Now here in this lesson, we're not going to discuss the theory behind this confidence interval. The book describes it in detail as to where this confidence interval comes from. We're just going to define it here and then illustrate how to use it to do some calculations. Okay. So we start off with a number alpha between 0 and 1. And let x be the number of successes in n observed trials of a Bernoulli experiment with unknown probability of a success p. So let's stop there for a moment. Remember, Bernoulli experiment is some experiment where we have a series of trials. Each trial is independent. We have either a success or a failure in each trial, and in this case, the probability of a success is p. And so what we're trying to do here is to estimate this value of p, and we have n observed trials of this Bernoulli experiment. So then we're going to define p hat to be x divided by n. That's just the sample proportion. And let z sub alpha divided by 2 be a critical z-value as we just defined. So then this interval here is called a 100 times 1 minus alpha % confidence interval estimate for p. Now this formula may look, or definition may look a little bit scary the first time we see it, but once we get our data, p hat here is a number, and that appears here, here, and here, and then again the same places on the right hand side of this interval. N is a number, that's our number of observed trials, and then z sub alpha divided by 2, that's our critical value. And so we just plug in a bunch of numbers, we do the arithmetic, and we get our confidence interval. Now, some of these individual parts of this definition have some special names. So this term here, z sub alpha divided by 2 times the square root, we're going to denote e, and that's called our margin of error. The square root all by itself is called the standard error of the proportion. The number alpha is called the significance level. And then the number 100 times 1 minus alpha percent is called the confidence level. Now, confidence intervals are written in one of three equivalent forms. This is the form here that was given in the definition. It's the form that's used commonly by different statistical software packages. This here is the form that we're going to use when we do calculations. I like this form the best because I think it more explicitly says what it is we're trying to say. And then this is the form that's often used in the news media when they give polling results. They all mean the same thing, just different ways of describing it. So let's do an example of calculating a confidence interval. And then when we're done with the calculations, we'll talk about what this confidence interval means. So suppose that 383 out of 735 surveyed voters support a particular political candidate. So we would like to know the proportion of all voters that support this particular candidate. Using this information, we can get an estimate of that population proportion, but we want to get a measure of its accuracy. So specifically, we want to calculate a 95% confidence interval estimate for the proportion of all voters who support the candidate. And so we're going to do this in a series of 5 steps. The first is to define the population proportion being estimated. And when we define this proportion, we don't simply restate the question or restate the problem. We define what it is we're trying to estimate. In this case, we're trying to estimate the proportion of all voters who support the candidate. And we're going to denote that by lowercase p. Now we stress the word all here because we're interested in the population of all voters, not just the 735 in this sample. Next, we're going to calculate the sample proportion. And so in this case, asking these 735 people, that's a series of 735 Bernoulli trials. And a success here is getting someone who supports the candidate. So we have 383 successes. So we'll take that number of successes divided by the number of trials, and we get 0.521. That's our sample proportion. So based off of this, it looks like about 52% of the voters support this particular candidate. The third step is to find the critical value. Now, to find the critical value, we first need to identify the significance level. That's denoted alpha. Now, what we're given in the problem is to use a 95% confidence level. Remember, the confidence level is just 100 times 1 minus alpha. And so if the confidence level is 95%, that means alpha is 0.05. So then our critical value is z sub alpha divided by 2, which is z sub 0.05 divided by 2, which is z sub 0.025. So we look at that table of critical z values, and we get our critical value of 1.96. So no calculations need to be done there, assuming that we're using a common value of alpha. Fourth step is to calculate the margin of error. So here's our formula for the margin of error, and we just plug things in. Here's the critical value, p hat, 1 minus p hat divided by n. We do that arithmetic, and we cut 0.0361. Now from there, we calculate the confidence interval. And so here's the form of the confidence interval that we're going to use. The lower limit is p hat minus e. The upper limit is p hat plus e. And so now we just plug in our numbers. Here's p hat minus e, p hat plus e. We do that arithmetic, and here's our confidence interval. 0.485 is less than p, is less than 0.557. Now let's talk about what these different quantities mean. The margin of error is 0.0361. So we would interpret that by saying we are 95% confident that the maximum distance between the estimate of 0.521 and the actual value of P is no more than 0.0361. So this gives us an upper bound on that error, or that maximum distance between the estimate and the actual value of P, okay, at the 95% confidence level. Now here in a minute we'll talk about what that confidence level means. Now our confidence interval, P is somewhere between 0.485 and 0.557. We would interpret that by saying we are 95% confident that the actual value of P is somewhere between these two numbers, 0.485 and 0.557. Now, what's significant about that confidence interval is that the lower limit is less than 0.5. So what that means is that the true value of P could very well be less than 0.5. It could be as low as 0.985 at this 95% confidence level. Now, on the other hand, it could be as high as 0.557 at the 95% confidence level. And so the fact that this lower limit is less than 0.5 means that this candidate isn't necessarily winning. He or she may have less than 50% support. Now, one question we might ask is, what does that confidence level of 95% mean? Well, let's give a correct meaning, and then we'll give an incorrect meaning and talk about the difference between them. So the correct meaning is that if we were to survey many different samples of voters and calculate the corresponding 95% confidence intervals using the statistics from each sample, then about 95% of the intervals would contain the true value of P. So it's saying that if we did this process of going out collecting data and then calculating the confidence interval many times, then about 95% of our confidence intervals are going to contain the true value of P. Now, an incorrect meaning would be to say that there is a 95% chance that the actual value of P is somewhere between those two numbers. So why is this an incorrect meaning? Well, let's make a couple of observations. Number one, P, the population proportion, is a number. I don't know the value of that number. Nobody does, but it is a number. It has a single value. Okay? So that number is either between 0.485 and 0.557, or it's not. It's either there or it's not. There's only two possibilities. So there's no probability involved. P is either there or it's not. So there's no probability or chance involved there. It's either there or it's not. We don't know which, but there's no probability involved. Okay? So what this illustrates is that the confidence level refers to the process of constructing the intervals, not the intervals themselves. Once the interval is constructed, P is either in there or it's not. There's no probability or chance involved there. It's already been determined. Now, we don't know what that determination is, but it's already done. So again, the process of constructing the intervals means that, again, if we were to construct many different intervals, then at the 95% confidence level, about 95% of those intervals would contain the actual value of P. That's what the confidence level means. If we were to work at a 99% confidence level, well, then about 99% of our confidence intervals would contain the true value of P. If we worked at an 80% level, then about 80% of them would contain the true value of P. So last thing we need to mention here are the requirements for using this definition of the margin of error and the confidence interval. As we've pointed out many times before, you can't blindly plug any set of numbers into any formula and expect to get valid results. They're only valid if certain requirements are met. So in this case, we have three requirements. Number one, the sample must be random. That's always a requirement for using any sort of statistical tool. We need our sample to be random. Number two, the conditions for a binomial distribution must be satisfied. Remember, binomial distribution, you've got a set of n trials. They're independent. Each one is a success or failure, and the probability of success doesn't change. So as long as those requirements are approximately met, then this second requirement is satisfied. And then the third is that there are at least 5 successes and at least 5 failures in the N trials. And this third requirement is necessary to ensure that the sample proportion has an approximately normal distribution.